Hello again. Uh, this is the second part of the previous video that talks about internal forces, and in the previous video, the internal forces, I solved this problem here. Let me show you the problem. Here. Yes, we solved this problem here, and I show you that whenever you have a concentrated force applied at a point, after explaining everything that has to deal with the internal forces and all the cases and what happened and what they are used for, in that case I show you that whenever you have a concentrated force at one point, you have, if the problem is a real life problem, you have to do the cut before the application of the force and after the application of the force. And the difference between before and after, you see 7 and -1, is going to be 8. And why 8? Because 8 is the value of the concentrated force applied. And I told you also, please memorize this, put it in your brain, implant that over there, put that implant there, and I say wherever you have a concentrated force applied at a point, at that very same point, the shear diagram is going to suffer a jump in the same direction of the force, in the same magnitude of the force. However, the moment is not changing. And I told you, okay, now let's do another problem where you have a moment. And this is the problem that I'm going to solve for you, and this is the explanation that I'm going to give you right now. Let's go with this other example, this other beam. Now we have a beam here. This is a simple support, this is a roller, and then you have a force applied here of 300 Newton. And then you have another force here, no, another moment here now of 4 kilonewton per meter, not kk, 4 kilonewton per meter. 4 kilonewton per meter. This is the point A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Good. This is 2 meters, this is 2 meters, this is 3 meters. And guess what? What the problem is asking you to do? Calculate the internal forces. Weird, right? We are talking about internal forces, and the problem asks you to calculate internal forces. Calculate internal forces at what points? At the point B and at the point C. What are the internal forces? Remember, I told you in my vocabulary, axial shear and moment even are going to be part of the internal forces. So at B and at C. And the point B is located right here with the force of 300, and the point C is located right here with the moment concentrated over there of 4 kilonewton per meter. You know something? I'm not going to do point B because you have that already. We did that already. In the previous example, it's exactly the same way. You do it before, that means that you are doing a section before the point C. After calculating your reactions, of course, you're going to have this with your reaction here, AY. You're going to do that, and then you're going to calculate this shear at B, a moment at B. I'm not putting even the axial again because I don't have any axial force. And then you are gonna do this case also with the force of 300 newtons here. My reaction AY, this is 2 meters, this is 2 meters, and this is the VB after the point C, after the point B. You can put to the left, to the right. If you want, you can put a minus and a plus here, just to tell you, oh, minus means to the left and positive means to the right of the point C. This is nomenclature. This is whatever you want to use. And same thing with the moment B plus after the point, moment B minus before. But you do this. You use the summation of forces in Y equals 0. After you calculate AY plus AY minus BB equals 0. Summation of moments. And that's it. You do that, please. Now what I'm going to do is calculate at the point C, because I want to explain you what happens when you have a concentrated moment. So first thing first, reactions. How do you calculate reactions? Well, I can do summation of forces if I want to, But I know if I do summation of forces, this is a pin support. It's gonna have AY and AX, which if I do summation of forces, I know this is gonna be 0 because there's nothing else in X. And here I'm gonna have DY. DY sounds like DUI. Don't get one, please. So DY. I do summation of moments, let's say D. Summation of moments at D equals 0. Why at D? Well, because I don't even want to calculate dy. I'm going to use the other side of the beam or whatever. You can do it at A, you can do it at B. Summation of moments at here equals 0. This is positive. This is going to be AY multiplied by 3, 5, 7, 7. If I'm calculating this point and applying this force, this is rotating in that way. That way, according to this, is negative. Negative. Now I go here and have this force of 300. 300 multiply vertical force, distance horizontal 5. Put my pin over there, apply my force, rotation in this way. That is positive. Now this moment is 4, but it's not 4, it's 4,000. And this is one typical error that people do. 4,000 kilonewton, now it's 4,000 newton, multiplied by what distance? And a lot of people do that and multiply that by 3. You don't multiply a moment by any distance. That doesn't have any meaning. The moment is already created there. So it's only 4,000. Anything else, positive or negative, is going in this way. This way, is rotating like that, right? And that way is 4,000, which is negative also. Anything else, anything else, anything else, anything else, nothing else equals 0. From here you can solve for AY, and AY, where's my calculator, because I don't have that solved here now. This is equal to 300 times 5 minus 4,000 equals 2,500. 2,500 divided by 7. 2,500 is 357.14, and this forces is in Newton. And this is the second typical error, because you know something, people calculate this, pass it to the other side, and forget about this negative sign here. So this is negative. What does this negative mean? That negative means that AY is 357.14 Newton, but it's acting not like that. It's acting in this direction. And you know something? Immediately, don't waste time. Don't say, oh, I will do it later. I don't need to do that. I'm superhuman. I forgot. I won't forget that. Do it and do it. Change the direction immediately after you do that. In that way you remember it, because it's written. You know, words are gone with the wind. Whatever is written there. This is the right direction for that. And now if you want to, you can do summation of forces in Y equals 0 if you want to. And then you say, why you gonna say if you want to so many times? Because I might not even use that, but I'm gonna show you a way that you could use that, and it was actually simpler if you want to. But summation of forces in Y equals 0. Then you have negative 357.14 minus 300 plus dy equals 0, and that value will be 657.14, and it's positive. That means that the direction we assumed at the beginning was the correct direction. Good, very good. Okay, 657.14. Nice. Now, the point has come in our lives that we have to make the important decision of what should I do with this, with the point C. Big question, big step in your life. Should I include the moment, or shouldn't I include the moment? And the answer is yes and yes. Yes to both. So let's do the first part. Let's first do the cut just before the moment. Just before the moment. If I do that, just before the moment, this is gonna be my point C. My force of 300 is here. This is my reaction. You see why I changed the direction, because if I put it up, I'm gonna keep putting it up here, and it's not up, it's down. And this is 357.14, and my distances are 2 meters and a little bit less than 2 meters for the math freaks. There you go. I have that over there. And now I include my internal forces. What are my internal forces? Remember, positive direction, positive convention, V sub C, and you can say before the point C, to the left, to the left, to the left, if you want to. And then you put here my positive direction for the moment to the left of the moment of the applied force, or to the left of the point C. Now you have that. And then you can say summation of forces in Y equals 0. And when you do summation of forces in Y equals 0, you have negative 357.14. What else? Negative 300. Negative VC equals 0. VC equals negative 657.14. What does that mean? That negative sign doesn't mean that I'm going to change the direction of the internal force. I cannot change the direction of the internal force. The internal force is created, is there, exists. The only thing that I do is that I know that force is negative. So when I do my analysis, my design, my elements, my stirrups, my section, my everything else, I have to put my shear as a negative shear. But this is not the statics, these are future courses. But you keep it like that. Now, you do summation of moments where at C equals 0. What do I do there? I have 357.14 times the distance, which is 4. If I put my finger here and apply my force, this is going to rotate in this way, and according to this, this is positive. Now, what else do? You come here and say this 300 times this distance is 2. Same thing, apply the force, rotates in this way, positive, plus MC equals 0. That means that my moment is going to be negative 657.14. No, what is that? Moment is equals to 357.14 times 4 plus 300 times 2, 600 equals 2000, negative 2028.6. What units? What units? What units? Units are Newton meter. Newton meter. That's the moment. What does that negative moment means? That negative moment, if you remember or you watched the previous video that I did, that means that if you have a beam like that, for example, in that beam at that point C, if it's negative, the positive way for a moment to deflect is this: compression at the top and tension at the bottom. That means that at that point the moment is acting with tension at the top and compression at the bottom. It's like an inverted shape, like this one. But once again, this is not for this class, this is for future courses, so forget about that. If you can forget about that. I know that if I was a student and the professor mentioned something like that, I wouldn't even sleep until I found that thing. Okay, so done. Now cut just after the moment, or the point C, if you will. In this case, the moment was considered that it was applied. It wasn't applied. Now I'm gonna do the same section, exactly the same section that I did before. What is the difference? This value is the same. This force is the same. Now we have a moment applied here of 4,000 kilonewton meter, newton meter, sorry. Distances are the same. Math freaks, 2 plus differential if you want to. They always correct me that. And by the way, my vocabulary freak is not a bad word, it's a good word. So I do my VC here, positive direction, assume all the time. After, that's when the plus, this is my convention. I use that because I wanna be sure that where I'm doing it. And you do the same thing. Summation of forces in Y equals 0. Then I have negative 357.14, negative 300, negative VC. This is the moment I don't include it in my summation of forces equals 0. VC after equals negative 657.14 Newton. Well, that's weird, because we got the same value before, so the moment is not affecting at all the shear. No, it's not. At that point, your shear diagram isn't going to suffer for the application of the concentrated moment. Remember the other time, the concentrated force made a jump in the shear diagram and didn't affect the moment. Now a concentrated moment, like this case, is not doing anything at that point to the shear diagram. Let's see if it does something to the moment then. There's a summation of moments at C equals 0. Then if I do that, then I'm going to have 357.14 times 4 positive plus 300 times 2 positive. Now I have this 4,000 applied here, negative. Oh, if I take moment there, does that moment produce moment? Yes, of course, it's a concentrated moment, it's already there. The distance is 0, but I don't need the distance for anything in the moment. So 4,000 plus NC equals 0. And NC is going to be equal to 1,971.6 Newton meter. And I'm so fast calculating this, you see. You know why I'm so fast calculating this? Because I didn't calculate it. I just say, you know something, there is a concentrated moment here, and I know for sure that before and after the application it should be a value of 4,000. This is what we got before, and this is what we got after. If you check the distance between these two, or the absolute value between the two of them, one is negative 2028.6 and this is 0.4, I'm sorry, 0.4, 1971.4, because they have to add 4,000. This is the way. So what happened there, whenever I have a concentrated moment, the shear diagram doesn't suffer, or the shear at that point doesn't change. However, the moment jumps in the same direction, in the same amount of the moment. There was another question that you should have done before. Why? Usually you ask that question always before the fact. Why? And here is not the exception. Why? Why what? Let me tell you why what. Why did I use this section? Because, you know, if I make a section at C, I could have used the other part. I use this part without the moment. That means that the moment was in this side, 4,000, and this distance is 3, and this is dy, dui 657.14. However, this is easier. I mean, if you want to use this side instead of using that side, it's gonna be shorter, kind of. However, the only difference that you have to pay attention, or the only other thing that you have to be really careful, is that, remember the positive convention in this side. If I'm gonna use this side of the beam, the positive convention is going to be this one. as I explained before. Now if I do this, I can do summation of forces in y equals 0, and I have BC plus 657.14 equals 0, VC equals negative 657.14 Newton, which is the same value that I got before. And if I now do summation of moments at C equals 0, then I have, and I say this is positive, then I have negative NC, negative 4,000, negative 4,000, plus 657.14 times 3 equals 0. How much is this? 4,000 minus, passing to the side, 657.14 times 3 equals 2028. Let's see, equals 2028.4 negative 0.6 Newton meter negative, which is the same value that we got before in the other way. You see? But somehow this is shorter, in my opinion, at least, than the other. Now if I want to consider the second case, which is this case, well, in this case the moment, I include the moment, meaning if I'm gonna use now for this same case in the other side, I'm not putting anything because the moment is in this side of the beam now. If I do that, this value is 657.14. This is 3 meters. The moment is not in this side, it's in the other side of the beam. And I can put here my VC and my MC. And I do the same thing. Summation of forces in Y equals 0. VC equals negative 657.14 Newton. And if I do summation of moments at C equals 0, then I have that negative, and I say this is positive, then I have negative NC plus 3 times 657.14 equals 0. MC equals 3 times 657.14 equals 1971.4 Newton meter, which is the same value that we got before. Summarizing, whenever you have a concentrated force applied at the point, the shear is going to jump in the same amount of that concentrated force, of course the concentrated shear force, and the moment at that point isn't going to suffer any change at that point. However, whenever you have a concentrated moment applied at a point, the shear at that point isn't going to suffer any change, and the moment is going to suffer a jump, the moment diagram, at the very same point, in the very same direction of the moment, in the very same magnitude of that moment. See you next lecture, guys. I hope that you enjoy. Keep studying, and studying. Have a nice day.